Let's identify a tree. No, not that kind of tree, silly. We're talking about graphs. So when we talk about graphs and the idea of a tree is a connected graph in which there are no circuits. Well, what is a circuit? A circuit is a path that starts and ends at the same vertex with no edges repeating. Okay, so that makes sense. Now, the number of edges in a tree is always one less than the number of vertices. So if we count the number of vertices, count the number of edges, make sure there's no circuits, that's how we can tell if we have a tree. So, some examples. Here on the left, you can see we have this lovely item, and we have 1, 2, 3, 4 vertices. We have 1, 2, 3 edges. So you can see the number of edges is one less than the number of vertices, and there are no circuits, meaning we cannot start with one and end in the same vertex going through no repeated edges. Same as the one on the right. We have 1, 2, 3, 4 vertices and 1, 2, 3 edges. Same idea. We can't start and end in the same vertex without repeating edges. So these are both examples of trees. So is the following graph a tree? Well, it's very pretty. A, B, C, D, E, F, G. So let's count the number of vertices. 1, 2, 3, 4, 5, 6, 7. 7 vertices and 1, 2, 3, 4, 5, 6 edges. Well, that satisfies. Can we draw a circuit? No. No matter where we start, we would have to repeat edges to get back to our beginning. So yes, this is a tree. What about this one? Is this a tree? Well, we have 1, 2, 3, 4, 5, 6 vertices and 1, 2, 3, 4, 5, 6 edges. Right there, that tells us this is not a tree. You can also see we have a circuit, right? Because we start and end at the same vertex. And therefore, no, this is not a tree. Maybe I shouldn't use that. This is not a tree. All right, so that's the idea of a tree, how we use it, how we identify it, and there you go.